back to a lecture series on hydrogeology. So in this lecture, we are now going to discuss about the groundwater exploration by geophysical methods. There are many methods are available for estimating or for locating or for understanding the subsurface variation in terms of groundwater, resistivity, seismic, magnetic and gravity. So among these four methods are exclusively used for this purpose, and these two methods are well proven method and most dominant method used by the many scientists. There is a photograph. All these four methods are being used. It's focused over here. The subsurface is taken as a cross section from the topsoil thickness. So the energy, whatever you do when you send electrical signals, it is passing on to the various layers and then touches the water table, or the magnetic or the seismic sound. If you send, it will behave differently in the different lithology of the subsurface, and in turn will be able to assess the groundwater at what depth, or the probable possible depth of water table is assessed by this method. Geophysical investigation, geophysical methods or indirect methods. It is not directly giving you, it is indirect methods which does not involve drilling. Of course, it doesn't involve. It is only assessing by the physical characteristics of the subsurface where the water is there. So when it interacts with the water, it will behave differently. Then we'll have to locate that particular point. The method comprises the measurement of signals from natural sources as well as induced phenomena of physical properties of subsurface variation. So as I said, it is indirect method. You are now sending the signals into the subsurface and assessing the subsurface formation variation. Exploring the groundwater by geophysical method. When you use this method, it is termed as groundwater geophysics. Many methods are available. As I said, four methods we have already discussed. The recent method which is being popularly used by many scientists for all applications in geology is GPR, ground penetrating radar. Yes, it has extensive applications in geology in terms of water, in terms of mineral, in terms of other resources present below the surface, as well as for natural disaster management studies. Among all, I said only these two methods are well proven method and widely used method with respect to groundwater is concerned. One is electrical resistivity method, the other one is seismic refraction method. In hydrogeology, geophysical prospecting can help. So it can help to locate the beds and fractures, to estimate the depth of the aquifer and water level, to determine the lateral extent and thickness of aquifer, to estimate the quality of water in terms of water salinity, to evaluate the total porosity and that water stored in an aquifer. And this is also helpful to determine the aquifer connections and to trace subterranean streams present below the surface and to locate the origin of thermo-mineral water. So it has plenty of applications. It is listed here with respect to geophysical applications. Why this is considered as most important for geological studies. Now we will discuss the electrical resistivity method. What is resistivity? Resistivity is the resistance in ohm meter of a unit cubic of material. Resistivity is always termed is the resistance in ohm meter. Ohm meter, this is the representation of resistivity of a unit cube of material being used to assess this. So according to Ohm's law, resistance R is equal to small v divided by small I. V is the potential difference in volt, I is the current in amperes. So the volt difference over the current which you send to the subsurface is called as resistance. Resistivity normally measures the apparent resistivity. It means you are not exclusively using only one formation, you are using different formation in the subsurface. So you are now taking the apparent resistivity. It means cumulative effect of all the formation subsurface of the ground to direct ground current DC flow. Resistance is the inverse of conductance. It is the inverse of conductance. This method is most common method for groundwater exploration. Electrical resistivity is the resistance of volume of material to the flow of electric current, which we have discussed above. Current is introduced in two different electrodes at the outside, A, B, and once if you send the current, then you will have to see the potential difference or the current movement if any drop is there with respect to the current which you have sent. So the difference of current voltage in terms of potential is measured in between in the central electrode Mn. There are two methods. Of course, now many methods are available, and the proven method given by the scientists Werner and Schlumberger, in their name it is given, Werner arrangement and Schlumberger arrangement. So this is Werner arrangement. There are four electrodes are kept in equal distance. Here this is Schlumberger arrangement. There are four electrodes are kept at different distance. P is the potential electrode and C is the current electrode. Normally this potential electrode is kept constant, and then current electrodes is kept to move up to 5 times, or if you get very low potential difference, then you will have to change the potential electrode. So the current is passed from one electrode, and then current is always moving with the harmonic sinusoidal fashion in the subsurface as a concentric circle. So this will move from plus to minus, and then after that, after touching then the voltage difference is being recorded here. So this is called the Schlumberger arrangement, and this is the Werner arrangement. Here you move the electrodes. Suppose if you are moving 10 meters, then you have to move the potential also 10 meters. What does it mean? It means if you extend the electrode, it means the interpretation goes beneath the surface. At a deeper depth we investigate. That is the concept. Once if you extend the electrode, it means you are not extending electrode laterally, you are extending your assessment in the deep depth. So the depth assessment is increasing at every point of movement. So this is resistivity meter. This is terminal is kept over here. Electrode is connected, current electrode to send the signals, and the potential electrode is kept in between to assess the difference. Resistivity meter is basically a current meter and voltmeter all in one. So the potential electrode, and here the voltage difference, current here from the battery we are sending the current, and ammeter is kept here because to control the current to send the subsurface. The lines which it moves, you know that this is called current lines, and the distance between these two is equipotential lines. Now let us discuss about the Werner array, electrical resistivity method of Werner array. In Werner array, there are four electrodes A, B, A, M, N, B. A, M, N, B. A, B are current electrodes, M, N are potential electrode. You see it is mentioned current electrode, potential electrode, and this is ground surface. I is the ammeter, delta V is the voltmeter assessment. Two electrodes are kept outside, that is AB, and two electrodes are kept inside, two inner electrodes, that is M1, or potential electrodes and current electrodes. So in this array, the resistivity of subsurface is found by increasing the distance between the electrode. Yes, the resistivity of subsurface, as I said, if you move the electrode laterally, it means you are investigating in depth. Suppose if you are moving 100 feet, means 100 feet you are going down, or 100 meter, 300 feet you are going down. This method is called vertical electrical sounding. So at this point the investigation is being done. So at one point, that is called, it is West method, electrical drilling. Detection of horizontal changes of resistivity is achieved by moving the four electrodes. You will have to move four electrodes, then only you will be able to detect the horizontal, the resistivity changes in the subsurface. And in this, it is Schlumberger array. Of course, here in the Schlumberger method, the potential electrodes are installed at the center, Mn, of the electrode array with a small separation. You see, the separation between the voltage electrode is very small, typically less than 1/5. So suppose if it is 1 meter, this will be a 5 meter, 1/5 of spacing between the current electrode. The current electrode are increased to a greater separation during the survey. You can increase until you get very low potential difference. while the potential electrodes remain in the same position. You don't need to change the inner electrode until the observed voltage becomes so small. If it is so small the voltage, then you will have to change the voltage V also to a certain extent. Now let us discuss what is the advantage and disadvantage of both. Here you have to, in a Schlumberger method, you have to move only two electrodes. I mean, only the two current electrodes. So it will, it will reduce the workload of the manpower. This can significantly time also. It will you will get time consuming factor as well as man consuming factor. Here you will have to move all electrodes. Two current and two potential must be moved to acquire each reading. Because the potential electrode spacing is small compared to the current electrode spacing, for large current electrode spacing, very sensitive voltmeters are required. Because you are not changing the voltmeter, here what is required? Very sensitive voltmeters are required. Here you are moving both together, so less sensitive voltmeter is required. Here potential electrodes remain fixed locations. The effect of near surface lateral variation in resistivity are reduced. Because all electrodes are moving for each reading, this method can be more susceptible near surface lateral variation. So this near surface lateral variation could potentially be misinterpreted in terms of depth variation in resistivity. So here the lateral variation in resistivity are reduced, but it is not reduced here. In general, interpretation based on DC sounding, direct current sounding will be limited to simple horizontal layer structures. Interpretation based on DC sounding will be limited to simple and horizontal. Both things, because of the resistivity method, it is limited. And what are the different resistivity values it is given here with respect to different formations like alluvium. The resistivity of O meter is between 10 and 800, 10 to 800. In sand, it is between 60 to 1000. In clay, it is between 1 to 100. In groundwater, it is between 10 to 100. In sandstone, it is between 8 to 4 into 10 to the power of 3. And in shale, it is 22 to 20 into 10 to the power of 3. 50 minus 4 into 10 to the power of 3 in limestone. In granite, it is between 5000 to 10 lakh. So this is the resistivity variations normally will expect from the different occurrences. So with this, the lecture is come to an end. Thank you very much.